So let's see, for 1a, we have p of 2 plus r of 0 minus q of 4. So if you go to your map, p of 2, go to function p, and then plug in 2, and you should get back negative 2 plus r of 0, go to function r on the map, plug in 0 for x, you should get back negative 2 for y, minus, go to function q, that we were doing last time in class, plug in 4 for x, and the y coordinate should be negative 2 equals. And careful with that double negative, which becomes positive. So we have negative 2 minus 2 plus 2, which of course is just negative 2. How about 1b? So we have 4p minus 6r of 0. That's the question. But this here, that happens to equal 4 times p of 0 minus 6 times r of 0. So keep the 4, multiplication. Now p of 0 is, I'm looking at the map, p of 0 should be negative 4, like that. Take away 6 times. R of 0 should be negative 2. So we have negative 16. And then double negative becomes positive. 6 times 2 is 12. So that should be negative 4. And then how about 1c? So 1c, we have p times q times r of 1. So this is p of 1 times q of 1 times r of 1. And p of 1 is, that one looks kind of weird, doesn't it? P of 1, I suppose this is the time when you would have to write the equation. Let me see, how about, yeah, and also for q and also for r. Well, tell you what, check this out. This is kind of like a sneaky question. And I almost, you see, I wrote this worksheet a long time ago, and I almost fell for my own trap. You see, P of 1 is kind of weird. If you look at the picture, Q of 1 is kind of weird if you look at the picture, but R of 1, go to the picture and go to R, which is the blue one, and go to 1, plug in 1 for X. If you do that, you get back 0 for Y. So it doesn't matter what these numbers are, because they're going to be multiplied by 0. So the whole thing is just 0. So that's good. That was kind of sneaky on my part, especially because the 0 was at the back. You see what I'm saying? So it would have been, excuse me, it would have been kind of annoying if you found this and this, and then it was just a 0 at the end of the day. So if ever you see a problem like this, take a quick glance at all of the pieces and see what happens. So I also want to try, let's skip down to 1F, because I think we tried some of the other ones together. So let's skip down to 1F. And it says, I'll try it on another paper here. So for 1F, that's an F right there. Let's pretend that's an F. We have parentheses, R composed with negative P over R times negative P, all of this taking place at 2. So let's see what this is. This can be rewritten as follows. The numerator is a composition. So the numerator is R of negative P of 2. And the denominator is multiplication. So that's R of 2 times negative P of 2. And let me just go equals here. So let's see, let me focus first. Let me grab a blue marker here, I suppose. I think you guys can see the contrast. So let's focus there on that blue there. How much is P of 2? So the negative is just negative, but how much is P of 2? So go to the picture. I'm looking at the picture, and P of 2 should be negative 2. So here's what I have. I have R, and I have negative, and then P of 2 was negative 2. If you want, you guys could put a 1 right there and put a multiplication symbol. So there's a negative 1, and there's my multiplication symbol. And in the denominator, we can multitask this afternoon. in the denominator, r of 2 is negative 2 times negative, and then p of 2 is negative 2. So there's another double negative happening, so that's positive. And this is, in the numerator, I have negative 1 times negative 2, which is positive 2. In the denominator, I just have negative 4, just a number. So now let's look at the numerator, r of 2. r of 2 should be negative 2 over negative 4. So final answer, 1/2. What about, let's see, what about the equation? How about number 2? Again, I'm not going to try all of them, but how about number 2, green? So 2 green. And that's a cube root function. So recall, for cube roots, we have the following equation. This is our cube root. And our hk is going to be the inflection point, which they tell us is 2, negative 3. So let's plug that in for h and k. So we have like that, we have like this, we have x minus 2 minus 3. Now we just have to find the value of a. And what's the random point? We have a random point at 10, 5/3, and that goes in for x and y. So let's drop in these numbers here. So I have 5/3 goes in for y, a stays a, cubic root, x becomes 10. Let me add the 3 before I forget to do so. Let me add the 3 there. So these are gone. And 5/3 plus 3 should be 14/3. I believe that should be 14/3 times a times the cubic root of 8. And the cubic root of 8 is 2. So I have 14/3 equals 2a. And we can multiply by 1/2. We can multiply by 1/2 here times 1/2 there. So these are gone. And a is 14. If you reduce this, if you reduce the fraction, you should get 7/3. So a equals 7/3. And you and I can drop it off here for our final answer, which I'll write down here. Y equals 7/3 cubic root x minus 2 minus 3. Let me box this in, and then I'll get out of the way. So there's that. So that's what I got for 2 green. Now, what about, let me see. Honestly, I'm looking at number 3. That one doesn't seem too bad. If you want, I could help you with the table, and then you could go from there. So let me get this out of the way. So for 3, here is the table that I would do. Realize that for 3, your vertex hk is at -3, +5. So if you made a table, try to use 5 points. Is that 5? 1, 2, 3, 4, 5. And I would take my vertex and I drop it in the middle. -3, 5. And then pick things before like -4, -6. How about like -2 and 0? And then just plot these, get the y's by plugging these axes into the equation. And then you get some y's, and then you can go to the x and y axis and you can get a graph. And it should be somewhere like at -3, 5, 1, 2, 3, 1, 2, 3, 4, 5. The vertex should be there and it should open down, something like that. So I'm not too worried about number 3 because that one's not too crazy. For number 4, we did the x-intercept in class, but what about the y-intercept? So for the y-intercept, you set x equal to 0. So write down the equation yet again for number 4, but this time we're gonna plug a 0 in for x. You see that? I plugged in a 0 for x. And then because all of this side is just numbers, I am totally fine if you just type that into your Casio calculator. And if you do so, I believe you get -17/4. So the y-intercept should be located at 0, -17/4. If you want to do that by hand, that's totally fine. But why don't you just let your devices do this for you, right? So for number 4, That's our y-intercept. And number 5, true, false. Let's see. So for number 5, I mean, you obviously have all the answers, right? And I'm not looking at the answer key, but let me see. So for number 5A, a quad function always has exactly 2 x-intercepts. That's false. You could have something that looks like this that has no x-intercepts. This is a quadratic function of parabola. This doesn't have any x-intercepts. Something like this has only 1 x-intercept because the key word there is they said always has. It doesn't have to have 2 x-intercepts. It could. That has 2 x-intercepts, but it doesn't always have to have that. It just could. 5B. So 5A is false. 5B, a square root function could possibly not have any intercepts. That's true, because how about this picture here? How about a square root function that opens up and to the right? That does not have any intercepts because at no point does it cross the x or y axis. So that for sure is true, and this one was false. How about 5C? A linear function always crosses the x-axis. That is false. Here is a linear, let's say that's x and that's y. Here is a linear function. Check it out. That is a linear function. And it's horizontal and it's above the x-axis. So it never crosses the x-axis. So that is a good counterexample to disprove this statement. So that's for sure false. How about 5D? Let's see here. All cube root functions have exactly 1 y-intercept. That's true, because remember, for cube root functions look like this or possibly like that. They always have to cross the x-axis once and the y-axis once. Always, 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 for sure, without question. What about 5E? 5E, let's see, the expression f plus g of -7 always equals, I'll just put a question mark, always equals f of -7 plus g of -7. That's true. That comes directly from our identities that we discussed in class. This is one of the facts, right? This is one of our facts. So I'm going to call that true for us in this level of math. Later on in other math classes, things can get crazy, but for us, that's totally true. How about 5F? It is possible for f minus g of 3 to equal, question mark, f of 3 plus g of 3 for some functions f and g. So this can be true, it can. And here I'll show you an example. Why don't you let f of x equal, let's say x, and why don't you let, let's say, g of x equal 0? Here's a good counterexample. Or here's a good, here's a good example that shows that this can be true. Because for 5f, they're saying, is it possible? So the answer is yes, it is possible. So it's true, but let me explain why. Pretend that f is that and g is that. Let's focus on this part here. F minus g of 3. If you follow the definitions, immediately that's f of 3 minus g of 3. But what's f of 3? Go to function f, which in my random example, this is just a random example. All you have to do is show that the statement can be true. And it can be true if I choose these random examples. So f of 3, you plug 3 in there, you get back 3. Minus, go to g and plug in 3. If I go to g, if I plug 3 in for x, I get back 0. And then 3 minus 0 is just 3. So that was this. What about this? What's f of 3 plus g of 3? Well, plug in 3 in for f, here, and you get back 3. Addition, plug in 3 in for g, there, you get back 0, which is just 3, and it equals that. So these can be true. They don't have to, but they could be true. That's why 5f is true. And let's see. 5g, all cubic functions must enter quadrant 3 at some point. That's false. That's false because you could have a cubic function that looks like this. Check it out. You could have a cubic function that has an inflection point in quadrant 1. This will never ever bleed into quadrant number 3, which is here. So this is a good example of how a cubic function could escape quadrant 3. So that's why it's false. And then lastly, 5H, the expression f composed with g at 1 could possibly equal f times g of 1 for some f and g. So just my gut instinct says that this can be true. And I would just think of very, very basic, boring functions. How about something like, honestly, look, to just keep it simple, what if f of x is 0 and g of x is 0? Under these conditions, is that the same as this? Well, let's find out. Let's try this first. We know that f composed with g at 1 is initially f of g of 1. Now, if I plug 1 into g, here I get back 0. So this is f of 0. And if I plug 0 into f there, I just get back 0. So this gave me 0. What about this? Let's try it down here. F times g of 1, by definition, is f of 1 times g of 1. Well, plug in 1 into f, you get 0. Plug in 1 into g, you get 0. So 0 times 0 is 0. So these can be true, but they don't have to be. So I went through that quickly, I know. But let me know if you have any more questions, and I'll gladly revisit any of these concepts. So keep studying hard, guys, and I'll talk to you guys in class. So have a good day, guys. Bye.